Welcome to section 3.9, where we will talk about linearization and differentials. So what is linearization? Well, you'll see in a little bit that it's not anything complicated. Let's take, for example, the function y is equal to x squared. Now, what is the line tangent to the curve at 1, 1? Well, we use the slope point form, which means we get the slope, we got a point, and how do we get the slope? Remember, our wonderful derivative of y gives us the slope at the point when x is the specified value there. So let's try. We've got the point. So the point is 1, 1. And what's the slope? Well, we need the derivative. Y prime, because remember the derivative is the slope function. So y prime is equal to 2x, and you plug in the value of x equal to 1. So you substitute that into the derivative, and that's 2 times 1, so the slope is 2. Therefore, using the slope point form, the line tangent to the curve is y minus y sub 1 is equal to m times x minus x sub 1. And what is that? That's y minus 1 is equal to 2 times x minus 1. And just, solving for y is how we get that. That's what we get here. So that means it's y is equal to 1 plus 2 times x minus 2, right? So that's 1 plus 2x minus 2. Does that give us 2x minus 1? Indeed. So there. That's the line tangent to the curve at 1, 1. Now, what if you get a really, really complicated function and then you want to estimate or to find the value of the function, but it would be easier if it was just approximated by a line. Now think of this function y is equal to x squared and the line tangent to the curve. If we zoom in, let's see what it's going to look like. Right, here are the different, screen captures of the function at different ranges of the x. Here, this was graphed from -1 to 3. And that was just the graph that I showed you in the previous slide. Now let's see, suppose we zoom in from 0 to 2. See, the line tangent is really, from here to here, they're almost coinciding. Okay, let's look at keep on zooming in, and then we just look at the graph of the function from 0.8 to 1.2. And you see, gosh, there's not even a difference between the two. You can't hardly tell which one. Well, I guess you can see that there's the blue curve, and then there's the tangent line. Now, keep on zooming in. So this is at 0.997 up to 1.00. I believe that's 1.003. You see, gosh, there is no distinction between the blue curve and the tangent line. So here we've seen that we can approximate, that's what it is, we can approximate x squared in terms of a line. So what we can say is the linearized version. So the linearized version of x squared, our function, is now, it can be written as 2x minus 1. Near where? Only near the point when we have at 1, 1. Because, look, you can't use the same tangent line if we want to approximate, say, when x is equal to 2. Gosh, see how far apart they are. Okay? So if this is, that's 1, that's 2. And if you want to approximate the square of 2, and that's what you get. It's very far from 4. So that's not a very good approximation. However, if we are looking at, say, 1.001, then I can just plug in 2 times 1.001 minus 1, and that's the good approximation for x squared. You see that? So this is the same as saying that Right? So we can approximate, say, to approximate 1.0, say 1.001 squared, that can be approximately equal to 2 times 1.001 minus 1. And what is that? Okay, well, let's see. That's just 2.002 minus 1. That means it's just 1.002. Well, what do you think is 1.001? Well, let's see. 1.001, and then we square it. What do we get? This one is exactly equal to 1.002001. And that means, wow, that is really a good approximation to this number. Because what is their difference? The difference is just in absolute value would be 0.00001. Wow, that is really a good approximation. So you see, the linearized version is a good approximation whenever you are in a local area. So what did we do? Let's just go back and see what we did. Right, to linearize a complicated function f of x near a point, it's got to be local. So we have to look at near a point A, say x equal to A. You take the function, that's the first step. Take the function, evaluate at A. So you plug in A into there, you get the y value, which is f of A. And then remember, whenever we need a line, we gotta have a slope. So we take the derivative, plug in A into the derivative, that's the slope. Use the slope point form. But now we're just going to rename things. So instead of writing it as y minus y1 equal to m times x minus x sub 1, now we will just make it sound fancier, I guess. We let y be equal to L of x. That way it will distinguish from the original function y. And then minus, what's y sub 1? There's our y sub 1. Remember, this is like our x sub 1 and then y1 in our slope point form. So it's just going to be f of a equal to, what's the slope? It's f prime at a. And then x minus, what's x sub 1? It's a. And then all I did is just transpose f of a to the right hand side, and there is our linearized version of a complicated function. Okay, so that's how it looks like. So it's really just your line tangent to the curve. So a linearized version of a complicated function is simply the line tangent to the curve at the local area where it's occurring at x equal to a. Alright, here is a really complicated function. Look at this. F of x is equal to x cubed plus 4x squared minus 3x plus 2. Suppose we want to look at the line tangent to the curve at x equal to 2. So when x is equal to 2, what is y? Y is 20. Well, all you have to do is just plug in the number 2 in here. So this is 8 plus 16 minus 6 plus 2, and you'll end up getting y equal to f of 2 equal to 20. So this is our a, and that's our f of a. And then what do we do now? Well, what's the derivative? F prime of x is equal to 3x squared plus 8x minus 3. So what is f prime at 2? That's the slope. Well, you just substitute. That's 3 times 4 plus 8 times 2 minus 3. And what do we get? That's 12 plus 16. That's 28 minus 3. You get 25. So that's the slope of this line. So what we have now would be, let's now rewrite this as, recall our y is now L of x. It's equal to f of a. So what is f of a? It's 20 plus 25, that's the slope, times x minus 2. That's just rewriting it that way. Alright, so what does that look like? Well, we can really just write it down, and it's gonna be I would like to leave it this way, and I'll tell you why. Right, so it's now this line tangent to the curve is this red one. Okay, it's the red line. And you see that as long as we are making an approximation close to 2, the line is almost coinciding with the blue curve. And if we zoom in, right here, this is just zoomed in from, say, let's try from 1 to 2, or even from 1.0 to 2.4, how about that, or 2.2. Rather, the blue curve is really approximated, it's coinciding with the blue curve. Well, let's see, let's keep on zooming in. Right, so we started with this function there, and then we zoomed in, and look, if I zoomed in between, say, 1.95 to 2.05, look, you can't distinguish the two. That means the difference between the blue curve and the red curve, the red line rather, are indistinguishable. You can't pick them out from each other because they're really almost coinciding. Well, this just tells us that instead of plugging in the value of, say, I want to evaluate at 2.1, instead of plugging it into the original function, which is, what is the original function? Well, let's write it down. Okay, our f of x is x cubed plus 4x squared minus 3x plus 2. Okay, this is now approximated, see, this is now approximated by the function 20 plus 25 times x minus 2. See, it has to be close to 2. So if, say, I want to find the value of, let's try 2.1. Okay? So at 2.1, what is the actual value? So if we had used our calculator and everything, it's going to end up looking like 22.601. Now, if I had used, if I had used the linear approximation, that means I'm plugging it into the tangent line, L of 2.1 is just what? 20 plus 2.5, 25 times, okay, I'm going to plug in 2.1 to the x minus 2. And that's where you get 20 plus, okay, what is 2.1 minus 2? That's 0.1 multiplied by 25, it's 2.5. And so this is equal to 22.5. Now you compare these two numbers. The difference is what? 0.101. That's not bad. Well, let's try even getting closer. Suppose we want to try, let's go to another slide. Or no, I can write it down here. So suppose we want to approximate what is f of 2.01. So see, that's 2.05, so 2.01 is right about here. Well, I can't really tell the difference, right? So what is the actual? So if we use that complicated function and plug in 2.01 in here, right there, okay, it's gonna look like 20.251001. Just use your calculator. Look, what is L of 2.01? That's just plugging in into the line right here. So that's equal to, it's easy, that's why I'm plugging it in here, because it's easy to see that that's just 20 plus 25. Okay, now it's 2.01 minus 2, isn't it? And what does that tell us? 2.01 minus 2 is 0.01. Multiply it to 25, that gives you 0.25. So add it to 20.25. Oh wow, look, what is the difference between these two? So when you take the difference, let's just put it in absolute value, okay? Their difference, f of 2.01 minus its linearized version, 2.01, is what? Oh, let's see. Take the difference between the two and you get 0.001001. That is pretty good. That means it's less than 0.001, or think about it, it's less than 10 to the, well, because of that 1 there, let's just say it's less than 0.10 to the minus 2, which is cool. That means they are less than a hundredth of a unit. So that's a good approximation. So which means if I even plug in 2.001 into the linearized version, their difference to the actual, it's even gonna be close to each other. So it's good. It's good to use a linearized version because look how easy I did. I was able, look how easy it was for me to plug in 2.001. I started with 2.1 and it was easy to evaluate instead of plugging it at each of these terms. Did you see? The linearized version, even if you're using a calculator, still this is quicker to find the value of this one. But it only works if it's a localized version, because I can't use the same tangent line to approximate, say, let's say 1.2 right here, because there's the linearized version and that's the actual version. That is a huge gap between the two of them. So we don't want it to be too far from 2. It has to be very close to 2 so that the blue curve and the red line are almost coinciding with each other. And this is just the graphical picture of how your linearized version looks like. And like we said, that it has to be localized. See, it's got to be localized in order to get a good approximation, to use the line tangent to the curve as a good approximation. It has to be very close to whatever A you have chosen.